Okay, so I think we are about 4 minutes early. And next, I'd like to introduce you all to John Ravi, who's a graduate student at North Carolina State University. John's going to present a VFD to allow data transfer between GPUs and storage without using CPU memory as a bounce buffer. And John, I'll hand it to you if you're ready.
All right, thanks so much. Let me start sharing my screen. And okay. Cool. Okay. So this is this work. My name is John Ravi, and this work I'm going to talk about today, I've done over the summer with my mentors Quincy and Cern at Berkeley Lab, and yep. So it's basically GPUDirect I/O with HDF5. So a little motivation before I get into the details. More and more applications are using GPU accelerators to accelerate their code, but the data movement to get the data to the GPU to start the compute is becoming more of a bottleneck. So there's this new technology NVIDIA is developing called GPUDirect storage that basically aims to reduce the latency for that data movement from storage to the GPUs. And in this presentation, I'll talk about what I developed to enable HDF5 to take use of this GDS technology and eliminate the CPU memory as the bounce buffer. So to go into more details about what that means to eliminate the bounce buffer, here I'm giving showing code of the traditional CUDA application that uses that basically leverages the CUDA programming model to take advantage of GPU compute. So here I'm just showing how to open some data, and so line 1 opens some data in storage somewhere, and then you allocate some memory in CPU memory, and you read the data into the CPU memory, and then you also allocate a GPU buffer using this CUDA malloc operation, and then you copy the data from the CPU memory into the GPU memory. And with GPUDirect storage enabled, you can open the file directly. In this case, you had to pass in this special flag to the file descriptor, ODirect, to basically disable the operating system's anything that it does, such as like caching or read ahead. And you still had to allocate the GPU memory, and then you can use the GDS API to directly read the data from the file system directly to the GPU buffer. So in this case, we're eliminating the CPU bounce buffer. Essentially, we don't have to allocate any CPU memory to buffer the data before it goes to the GPU. So that's the main idea. And for this work, I basically created a VFD, a virtual file driver for HDF5 to take advantage of this this API. And then this presentation, I'll also compare the performance with the default Sec2 VFD as well as the direct VFD. And the main differences between this GDS and VFD and the Sec2 VFD is that the file descriptor has to be opened with ODirect. And as I said, this disables all OS buffering. And this is one of the requirements to take advantage of the GDS API. And another thing is that the read and write handlers need to distinguish between the CPU memory and the GPU memory, mainly because currently the HDF5's metadata is stored in CPU memory still. So you're still doing some operations to the host memory when you're transferring data to the GPU memory. And another thing is that the file driver, the Ku file driver, which it's the NVIDIA driver that enables this GDS, needs to be initialized per run. So that's a little bit expensive too. And another overhead is, so to distinguish between the CPU memory and GPU memory pointers, I currently query the CUDA runtime to figure out where the memory pointers are allocated. And that happens for each IO request, and that can be expensive for smaller IO transfers. And lastly, there's this Ku file buffer register. Basically, at each IO request, the driver figures out that address translation from the virtual address space to the physical PCIe address space translation, and it will register that to the DMA controller. So if you're using the same buffer over and over again, you can avoid doing this translation at every IO request. So currently, I don't implement this reuse concept with this VFD, but that's another reason why there's some overhead with this implementation. So on top of this, I wrote some extra knobs to take advantage of, especially for Lustre file system. For example, I basically enable pthreads to service each IO request to HDF5, and each IO request to HDF5 is serviced by multiple threads, basically. So the idea is that like you can service each IO request and take advantage of the multiple storage devices in a Lustre file system, and do the IO requests concurrently faster. And another knob is the block size. So the idea behind that is you can like batch up the coup file request into smaller transfer sizes, so that if you match the stripe size, you might get better performance in that case. So before I go into the results, this is where I did some of the most of the experimentation. It was the NVIDIA DGX2 machine, and I was doing these experiments with a beta version of GDS, and it had both local storage and network file system. So for the local storage, it was RAID 0 to NVMe storage devices, and the Lustre file system with 4 OSDs and default stripe size. So for the benchmarks, I basically wrote sequential read-write rates benchmark, and which basically just measures how long it took to get the data to the GPU and get the data out from the GPU. And then for the Lustre file system, I basically wrote the same type of benchmark, but using multiple threads inside the VFD. And I also have one experiment which shows using multiple GPUs. So this is the local storage write performance. Here I'm showing the Sec2 VFD, using Sec2 VFD, Direct VFD, and GDS VFD. So with the Sec2, I do the IO requests and also use the CUDA memcopy to basically buffer the data into host memory and then transfer the data to the GPU memory. So there's some latency there. So the performance of that isn't as good as just using directly the GDS VFD. I'm also showing this pinned memory idea too. So with pinned memory, the idea is that you can basically pin the CPU memory so that the pages doesn't get swapped out. If you don't pin it, then the operating system, if it figures out that if it decides that you're running low on memory, it can decide to swap out the pages to swap. And to prevent that, like basically what the CUDA driver has to do if you don't pin it is allocate a separate buffer to buffer the data in there before it copies it to the GPU. So there's like an extra latency you're adding on top of that if you don't pin the memory. So I'm showing using pinned memory as well, and you can get a better performance there too. But with GDS, you'll get the best performance because you're eliminating that bounce buffer altogether. But you can see that for I guess smaller sizes, the GDS isn't as good. And this is for the reason why I mentioned earlier, some of the overheads, such as like querying the CUDA runtime and and also registering the buffer. It's expensive, especially for smaller IO requests. And this is for read performance for local storage system. And in this case, I'm showing those 3 VFDs as well. But I'm also showing read ahead enabled. So read ahead, basically, the operating system is prefetching the data. This is a sequential benchmark. So the operating system can prefetch the data and cache it. You can disable the read ahead, but basically using a system call, fadvice, and basically tell it to treat the IO request as random and essentially turn off read ahead. And read ahead is not enabled for GDS mainly because it needs to be enabled at the driver level, and it would need to allocate some memory on the GPU and start prefetching data there. And that's just something that NVIDIA hasn't done yet. So in reality, there's no prefetch read ahead happening. I just do the same like fadvice system call on it, just to make sure that you get the same performance there, right? And you can see that the same idea, this sec2 and so direct VFD already turns off like all buffering and read ahead. So it makes sense that like there's no read ahead going on here. So you get good performance with sec2 and read ahead enabled. But since you eliminate that bounce buffer again, GDS also performs best after a certain file size or IO size request. Same reasons why there's not as good as performance as sec2 plus read ahead, mainly because of that extra overhead I mentioned earlier. Here I'm showing the multi-threaded writes. So the subplots here is I'm showing like different sizes of block size, and then on the series here I'm showing multiple threads, and this is compared with the default behavior of sec2. So I didn't enable threading at all for sec2. So this dotted line here is just an overlay of sec2s with like a single write request. And you can see that it's much faster with using GDS and using multiple threads to batch this write request into multiple threads. So in this case, like if you do like 1 GB transfer and you batch it into like multiple threads, like each thread will do a smaller subset of the write, and you get much higher performance with the Lustre file system. I also did a similar study with the local file system, and like as expected, you don't get any benefit using multiple threads in the local file system, because at the end of the day, the file system will sequentially write to the storage medium. But in the distributed file system, you can concurrently write to multiple OSTs at the same time. And now I did the read as well. So in this case, I didn't have a chance to disable the read ahead, but because I didn't have access to the system for a very, very long period of time. So you can see that with sec2 it actually performs much better than using GDS, mainly because the read ahead was left on. And the main takeaway is that like if you use sec2 with read ahead on, like you'll get better performance for sequential IO requests. Finally, I'm showing multi-process like parallel IO requests using multiple GPUs. Again, so this work is mainly for sequential HDF5. There's another group doing enabling GDS for parallel HDF5, mainly using the MPIO VFD to get that to work. But to show like a multi-process example, I basically bind each GPU to a MPI rank and write to a single HDF5 file per MPI rank. So in this case, adding multiple GPUs, I can get a lot higher throughput, mainly because you have multiple data paths going to the storage system. And with the sec2 case, you're kind of limited by the latency from going from the GPU to the host memory, then to the file system. So using GDS is always a win when you're using multiple GPUs. And I also did the same thing with reads. Again, the read ahead in this case was left on, and you get better performance with sec2 and read ahead left on, mainly because it's sequential benchmark. So yeah, that's everything. The main conclusions is the write rates are really good compared over sec2 because we eliminate the bounce buffer, but the read rates in most cases is better with the default because especially for sequential. Because the read ahead and future work includes figure out how to like tune these knobs, such as the number of threads and the IO size requests for distributed file systems. And then also avoiding this, this overhead that I mentioned for smaller allocation sizes. So in that, I was thinking of like basically making the user explicitly state what type of pointer they're sending the IO request. So like, let's say it's the pointer is from GPU or from the CPU, so that you know how to query the CUDA runtime for that. And also track data buffer reuse, so you can eliminate the data buffer register, and asynchronous IO. And that's everything. Sorry for going over time.
Thanks, Ravi, or John.
Yes.
So I think there were a few questions, but I think Quincy and Elena may have answered Mark's questions in the chat. But if you have anything else to add.
I didn't answer. I'm confused, so I'm trying to clarify, but it's okay.
Okay.
We can have a discussion online.
Okay. So thank you again.